they sort of all fell apart. No, they actually came together recently, and it's kind of neat. So it's actually spanning almost the whole 7 years I've been here, which is kind of funny to give a talk at the end. What you call it, the famous TMU last lecture. I'm not dying this voice, I know. Yeah. So background, hopefully all you know this, binary decision diagrams, where you're representing Boolean functions very efficiently, have canonical representations, blah, 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 blah. They're very useful, used extensively in homomorphication, but they have uses the other places as well. The system that I built over many, many years, the whole system has these BDDs built in as first-class objects. So you can do simple things like variables, name some, you can build expressions, and you can compare them, and you can simplify them, and all kinds of fun things. That's nothing terribly interesting there. What's slightly more interesting in this idea of having bit vectors built in. Bit vectors is effectively a list of bools, or BDDs, except that they also can extend automatically. They are sign extend automatically. So if you're comparing an if then else, say, over some expression, it will automatically make them of the same length, so they can actually do the if then else, even over symbolic expressions. That's a very, very useful thing. So now you can write code that are rather funny. So here we have a count function that counts the number of ones. And if the list is empty, it's 0 into BB, that equals the bit vector for 0. Otherwise, if head 1 is true, then it's 1, otherwise 0, and they add the other ones. Except that the head of L might actually be a Boolean expression. It might not just be true and false. And it will do the right thing for all the symbolic expressions. So if you just give him zeros and ones, then of course it just computes it. But here's one that has variables in it, and it will still compute the right thing, except that now, of course, it becomes an expression. And cover all the possibilities there in one. That's very, very useful. And this is what we're going to be using quite a lot here. Now, this talk is about matrices. And representing matrices traditionally is, of course, that you store them in memory. All the elements are stored typically contiguously in RAM. And each element is stored somewhere in the RAM, and you can find them fairly efficiently. If the matrix happens to have certain properties, for instance, very sparse, you might have some more fancy ways of recording the elements, so you don't have to store lots of empty space in memory. But nevertheless, the actual elements tend to be stored explicitly. If you have floating point numbers or if you have integers, they are stored somewhere for each of them. And that's what we're going to start playing with here. And of course, all operations on the matrix, like multiplication or something of two matrices or a matrix and a vector, they have to look at all of them. They have to explicitly go through and check each of them and do whatever operation needs to be done on them. We'll now introduce a symbolic representation of matrices that instead of storing everything explicitly, has everything implicitly stored in the graph structure, effectively, in the BDD. And we'll do it by example. So, suppose we start here. Here's our initial matrix. Nothing fancy, I just picked some random numbers. They are really random, as you noticed. The first thing we do is just convert the integers to bit vectors, so BBs. So if you don't remember Boolean stuff, or bit vectors or tooth complement, if the first one is a false, it's a positive number, and then it's just binary encoding. And tooth complement is a bit more tricky to remember. I always have to think about it for a bit, but if you want to do it, you can just invert all of them and add 1. That gives you the value in the negative sense. Or if you fancy it, you negate everything up to the last one and keep that one. Same thing. So we convert it to BB, and the next thing we do is we introduce two symbolic bit vectors, one for the row selection and one for the column selection. So we're essentially going to use a bit vector to select which row are we talking about, which column are we talking about. And then we're going to say, build a BDD for each bit position in the matrix.
Why are there 3 elements in R?
Because I wasn't. Well, actually, we need it because we have.
Oh, here it's made for
this example.
Okay.
This example. So yes, thank you. Very good point. in general enough to fit the matrix. So we build that BDD.
Begs the question why the column has only 3 entries.
That is, it's 2 bits, right? There are 4 entries.
Oh, okay.
Yeah, so we can represent 0 to 3. It's column 0 to column 3.
Okay.
It probably wouldn't represent this in the actual code, but we'll ignore that now. For the simple example, I try to make it a bit simpler. I tend to have 1 extra because you want to have, if I'm outside the columns, you don't want to wrap around and do funny things sometimes. So that we sometimes play a little bit games. But anyway, for each bit position in the matrix, so for bit 0, for instance, if you looked at this one, well, it's bit 0, the least significant bit 1. Well, it's 1 here, 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 there, and there. And if you look at it right out, you can see if R is 0, row is 0, then it's a column 0 or column 2, etc., etc. Nothing strange here, just represented as a BDD. So if you did that for this example, you would get this BDD. The most significant bit down to the least significant bit. And these are the variables and these are the columns. Here I did all the row variables first and all the column variables after. Now, if you store this as BDD, in practice, you actually tend to use something called negative pointers. So I'm just showing you that one too. It just is a more efficient way. You can often reduce the size of BDD by a factor of 2. Effectively, you have red and the blue pointers. A blue pointer is normal pointer. A red pointer negates the meaning if you go down. That's all it does. But it makes it more efficient to store. You often get a factor of close to 2 at least. 1.5 maybe is more common. Okay, so now we got this one. Here's an example of matrices that are reasonably large, 100 by 100 up to 800 by 800. And what differs here is I decided what we look at what values are we storing. And I picked them randomly from within these ranges. Either they're basically 2-bit versions, 4-bit versions, 8-bit version, 8-bit versions. And this 11-bit versions. Effectively, what would you end up with? And notice that it grows. But it's also interesting to see that we actually use a sparsity in some sense. Here we have the sparsity not in terms of the values in the matrix, but actually the values. Here, for example, there are really, in this whole column, there are really only 4 different possible values. So we have the sparsity in the values as well. In fact, I didn't do it, but it would be interesting to do it, say, well, pick random values between 0 and 10 million, but we only pick so many distinct ones. That sparsity will also show up here, probably the BDD being relatively modest. What's more interesting is that if the matrix also has some properties. Here we have the dense one. Every cell has some random value. Here, even only the even columns have values. Here, only even columns and even rows have values. And the almost diagonal effectively is that values that are non-zero are within a distance 3 from each other. So effectively, it's a fat diagonal more than anything else. Notice how the representation collapses for those things. It becomes very small very quickly. So that's kind of nice to have those properties.
Yeah, but you should balance this with the ordinary sparse matrix.
Of course I should. The funny part here is that it can go from one to the other without changing the representation internally. BDDs will sort of do it. If you start with a dense matrix and multiply with something, it becomes more of a sparse matrix. That happens automatically. You don't have to say up front that, yes, it's going to be a sparse, so I have to use the overhead of sparse matrices, because there's an overhead to that. So here we sort of automatically have it. Of course, it's a heuristics, so your mileage will vary.
So Carl, I was just wondering about the density of storage. So imagine a dense representation of that first line there.
Yeah.
That has 640,000 elements, right? Yeah. But they're only 2 bits each.
Yeah.
Yeah, so
I can go my version be like this. Yes.
okay. So it's not smaller than the dense representation. It takes advantage of the bit size of the.
If you do that, you can store way more compressed values that take much less memory than this space. Yes.
Okay.
The the interesting thing is actually not to say this is not my argument for why using this as an efficient way of storing. It's an interesting way to store it. It's not horrible. What's interesting about what we can do with it.
Yeah.
That's what's coming. So, what can operation? I mean, storing something is not, it's good, but it's not very useful. So, if you want to get an element, it's trivial. You just do substitution for the values into the BV, and then convert it maybe to an integer if you actually want to see what the value is. So that's very easy to do. If you want to transpose a matrix, just substitute the raw variables for the column variables and vice versa. That's also very easy. If you want to add or subtract two matrices of the same size, of course, you can't do it any other, then you just add them, BV add. That's a very, very simple one, or BV subtract, either way. So that's nice and simple. And if you want to multiply a scalar value, then you just multiply with a scalar value. All nice and simple. But you can also do funny other things. If we come later, we're going to talk a little bit machine learning. So relu is an operation that you want to do on vectors, or matrices for that matter, or tensors, or whatever you want. In this case, just take the symbolic bit vector and compare it to 0. And if it's greater than 0, then it says some, otherwise it's 0. That's the definition of relu. It does it for every element in the matrix or a vector at the same time. So nice and simple. Now, at this point, I would be very happy. And then someone like John, what about multiplication of two matrices? Now we're getting a little bit awkward. There really is no good way to do this, at least at first. But actually, there is. So I'm going to do a bit of a detour here to get into thinking about this. So what we need, I realized after a while, is some kind of BV sum function. It takes a bit vector over some variables and computes what is the possible values if you add them all up, if you did all instantiation of those variables. We want to do a BV sum, effectively. So if you had this example we had earlier, this is very long delay, by the way.
Sorry.
If we do BV sum, yes?
Do you have time to explain, for instance, addition? Because I don't see it, how you do it on these.
I think of it as a circuit. It's just a circuit that does addition, like a ripple carry adder, effectively, of the two bit vectors. You take the least significant bit, you XOR them together, you compute the carry out by doing the majority of the two inputs. That takes
but I don't know how to do it on BDDs.
Yeah, so you just do those operations. The ANDs or XORs are just done on the BDDs. So all the operations end up being a whole bunch of Boolean operations with the BDDs. So addition, subtraction, multiplication, all the things turn out to be circuits effectively that are just done on the BDDs. Those operations. Does that sound clarify? Kind of, okay. So back to the BV sum. We want to add the BV sum, but all the possible values here. So conceptually, we want this. We want it V when we substitute 0, 0 for A and B, 0, 1, 1, 0, and 1, 1, and add them all.
Before you explain how you do it, why can't you do matrix multiplication by just doing matrix multiplication, unroll the loops and...
Oh, yes, I can, but then I would have to, of course, substitute all of them and do all this work, yes. But it takes an enormous amount of time.
Okay.
Yeah, yes, of course you could do that. But I'm trying to avoid doing it explicitly. In the game here is always trying to avoid doing anything explicitly and always do it implicitly. That's how we get efficiency. So here is the semantics more than anything else I'm saying. This is what I want the result to be. If I did this, I would hopefully get 14 as a bit vector. That's what I dream. I want to do this, but I want to do it efficiently. In particular, I want to do this without enumerating all these elements. And I actually want to do something even more. Here, I want to do BV sum over all the variables that occurred in this bit vector. But maybe there was another variable like C, and I didn't want to add over C. So I want to build something that generates a result that has a function over C. So this is my third requirement. This is what it should do without enumerating, but also work if I have some free variables. in the expressions. So now we're going to take a little this detour off into more interesting things. This is unusual for BDD-based things. And that's called model count. SAT, satisfaction, you all know what that is. That is saying basically, here's an expression, is there a solution? Yes or no? Model count says, how many solutions are there? Or how many models are there to satisfy this expression? So we actually have to say, not only yes, it's satisfiable, but it's how many ways can you satisfy it? So that is what, if in complexity theory, it's what's called a sharp P, number P, or sharp P number complexity class. And sharp P is in general really, really hard to conjecture to be significantly harder than NPR problems, which are already, of course, exponential, most likely. However, there are some good news. It's solvable in time proportional to the size of the BDD. If we can represent the expression as a BDD, then we can solve it very practically. Model count for BDDs is trivial, as I will now show. Here is a simple version of model count in FL. We take a bunch of variables and a Boolean function f. If we are done with all the variables, then we just need to look at f. Is f equal to t or false or 0? Is it true or false? If it's 1, then of course, if it's true, then of course we have a model. 1, add 1 to it. If not, it's 0. Otherwise, we'll just go down the variables. We substitute, if I have to think of it as a BDD, the left and the right side of the BDD, and we just add them up together with the left side and the right side, model count, and add them up. And that gives us the model count. Now, two things are problematic with this one. The first thing is BDDs, as I probably should have mentioned, is of course directed acyclic graphs. They're not trees, they're dice. What happens when you run this code? It goes out and treats it as a tree. So your small BDD ends up being exponential when you run it, because it treats all things as trees, as different. And that's not good. The other thing is, because for a lot of BDDs, there's a lot of spanning things. If edge goes from variable A down to variable K, and without going through B, C, D, and E, and so on and so forth. There's often a lot of big spans in BDDs that you want to not go through each of them. So it's not very efficient. So here's a better version. First of all, FL has these very beautiful things. If you add a C in front of letrec, it becomes cached, automatically memoized, without anything else need to be done. Very convenient. That's the nicest thing I have in FL. Until you tell that to someone, and the first thing they do is they do C letter on everything. And then they come back and say, my code runs much slower now. Why? Well, memorization isn't free. You have to actually compute the hash function for each, determine whether you computed it before or not. And if it turns out that there's no sharing, then you're just doing all this overhead without getting any results for it. So, but in this case, we do want to treat this as a die instead of a tree. Therefore, memorization is your friend. And then the other thing, for making it a bit more complicated, is we're skipping empty BDD levels. And just essentially do 2 to the k, when k is the number of levels we skipped, to multiply the values. So it's just a more efficient way. And if we run this thing, here I did the example, 2 bit vectors C and D, 4-bit numbers, and the condition just C is greater than D. And the unsigned, so let's see what does it mean. Well, if for that to determine that, if C is 15, then D can be 14, 13, 12, down to 0. Or if C is 14, then 13, If you look at that and rearrange on the blackboard or whiteboard for a bit, you will discover that you need to add 7 times 16 plus 8 if you do Euler's method. And it turns out to be 120. Yeah, that's what it should be, of course. It took me about 6 attempts before I got that answer. I'm not as smart as Euler, let's put it that way. That was much harder to do than I thought. But we haven't solved the third problem, the third constraint. Come on. We need the generalization. What if there are some free variables? And it's almost the same code as before, but we now have an extra argument, which is the free variables. And what we do, the main thing is really at the end here. That is, if it's a free variable, then it just becomes a condition. But if it's not a free variable, we just add them together. So that's really all it takes to do this in a BDD shape. So the model count is actually very efficient as a result. Here is an example where we actually give it the scalar values as before, and one below. Well, I should say one more thing. Of course, I can't return an integer because it's an expression. So I have to return a BD. That's the only thing that differs. But of course, it's the same result as before. However, if I now do one that has a condition that has some free variables, A and B are not free. So if A and B are both false, then the condition we want is C is greater than D. If A is false and B is true, then we want a condition that C is greater than D plus 1, and so on and so forth. So we have 4 different conditions here. And if I now do a model count on this and say A and B are free, I get this expression coming back, which you can look at and say, yeah. And you have no idea what it is. Except that then you say, enumerate some examples. I said, enumerate 100 of them, but there are only 4 of them. And why are there 4? Well, there are 2 variables, and we have 4 different possible cases. So if n equals 1, then for A and B equals 0, then we have C greater than D, which is the one we had before. So 120 is still there. But the other ones are slightly smaller with coverage. Now, then back to the BB sum. And XMB is not that difficult now. We have model counting for what we do now is we look at the bit vector and treat them each bit at a time and use model count for each bit position. Of course, it has to be multiplied by the position in the vector. So what you end up, here's the example of this. MCF is just a shorthand for the model count of A and B for F, just so we know what we're talking about. Previous example, F, A and B, not A or B, and true. Maybe some of that would be, well, the position in here, 0, 1, 2, 3, so 2 to the 3 times the model count of F, plus 2 to the 2 times the model count of A and B, plus 2 to the 1 is position now of A prime or B, and 2 to the 0 times model count of true. And if we plug our values, we see we get 8 times 0, plus 4 times 1, plus 2 times 3, plus 1 times 4, and we get 14. But we did this without actually having to enumerate anything. We just did model count on each of them, and each model count can be done very efficiently, in fact, time proportional to the size of BDD. So if the BDD for the B vector is reasonably large, reasonably sized, we can do the BB sum in the same time as the size of that, the BDD, the sum of the BDDs, the BDD tree, the tree forest, if the right terminology. So here's actually our BB sum. Except it has one little tricky part, which this works in positive numbers, positive BBs, start with a false. If it's a 2's complement, it gets lost, confuses. So we have to fix that later. But for the positive, this is all we need to do. We do the depends to find all the free variables. Depends just gives all the variables that BB depends on, and subtract all the variables that we want to enumerate over. That gives us the free ones. We do get the lists out from the BB, just the accessor from destructor function, effectively to the data type. We then select bits down to 0, gives it the powers of whatever it should be. And then for the power, we just take 2 to the power into BB, multiply that by the model count for that. So that's all what the code does. And then map 2 over the 2 of them, and then accumulate them all together. So here's an example. If A and B, then it's 7. And if not A, then 3 and 1. Cheating here, you can see what the answer is, but what is the positive BB sum of that? And if you didn't see the answer down at the bottom, what would be your guess? We have value can be 7 or 3 or 1. Why is it 14? Why is it 7 plus 3 plus 10?
2 times 3.
Do a 2 times 3 because we didn't say anything about what B was here. So B has both 0 and 1 there. If we wrote it up more explicitly, enumerate all cases with A and B, not A and not B, and not A and B, and of course the remaining. So then that's why we get 2 3s and 1 7 and 1 1. Took me a while to figure that one out. It's really hard to find bugs when there are no bugs, and you're convinced that there are bugs. I have to tell you that one. Okay, but we couldn't deal with negative numbers. Well, you can. You just have to be a little bit clever about it. So what we do is we compute a predicate that if the pass is pass, effectively, is B, if the BB is greater than 0, greater or equal to 0, then it's pass. And then we separate the BB into 2. One where we keep it as is, and the other one that we negate, or the negative one, we negate them. And what we do is we add the positives together, we add the negatives as positives together, and then we subtract the negatives from the positives. That's all it takes. Very simple. Why it takes me a week to figure that out, I don't know, but I guess I'm old. But anyway, doing this, you get now for the same thing as before, except we changed to -3 here. You get 2 to the -3, so -6 plus 7 is 1 plus 1 is 2. And that's what we get. That was a long detour. Hopefully I didn't lose you all together. So how do we do matrix multiplication now? Well, pseudocode is effectively the following. After all, what we want to do is we want to go over the first matrix for each row, we want to each column of the other one. So effectively the column of the first matrix in the row of the other matrix are needed to be summed up together. So what we'll do is we'll just rename the first matrix columns variables to some temp that is not used anywhere else. And we do the same thing for the matrix 2's rows. And now to compute them, we just multiply them, normal BB mult, and then call the result P, and then before BB sum over the temp variables. So effectively we add up all the internal results in between. John looks very confused.
And then you need to do that for all rows and columns.
That happens automatically.
So when I learned to multiply matrix 1 by matrix 2,
yeah.
matrix 1 is the left argument,
Yeah.
I would take the first row of matrix 1, multiply it by the first column.
Yes, so then you're adding them up together, right?
So I would expect you to be taking the row variables in matrix 1, renaming them to some
No.
column variables.
Yeah, because think what you want to add together is as you go down the first row and the first column,
Yes, how many?
you get all of those
Yes,
together.
yes.
And that's the ones you want to add together.
Yes.
And that's why we do the column of the first and the row of the second.
Yeah.
2 new variables and add them up.
I agree.
So here's the code. A little bit more complicated because I introduced a data type so we can avoid some stupid mistakes like trying to multiply a 3 by 5 to a 12 by 9, which of course should not work. And I actually can error check that quickly now. So what it's doing, and actually what's really important here is sort of what I said before. You do a substitution and then you multiply them as a circuit effectively, and then you do BB sum of the dependence variables. And that gives you multiplication matrices, which is pretty cute. I have to say I was very pleased by this one. Performance example, of course, if it doesn't work, then it's not useful, but it works pretty well. Here are a couple of examples. 100 by 50 multiplied by 50 by 25. BD size time 1 and time 2. Time 1 is when I'm not cheating, and time 2 when I'm cheating. Time 1, basically, I just ran it with not thinking about variable orders or anything. I just ran it to see what let the system reorder if it needed. 2, take the time, the ordering you got at the reordering, and use that. So now, and I'm going to talk about that for future work, but clearly there is probably some pretty good idea how the ordering should be. I haven't spent time doing that yet, but I'm pretty sure we can come up with pretty good variable orders that are statically determined in advance. But
What's the units, the last 2 columns?
pardon?
4.6 what?
Seconds. No, days. No, it's all seconds on my laptop, on running a virtual machine. So it's not blindingly fast by any means. Although nowadays, I don't know if there's any faster machines available. To be really honestly, not much difference. So, X matrices, I think they're kind of used to represent matrices of any dimension of integer values. Actually, it doesn't have to be integers. You could represent floating point numbers at the bottom, or anything that you can map into a bit vector effectively. So you can actually have symbolic data types effectively at the bottom as well. You can do other operations you can imagine. But anyway, that's.
But the arithmetic would be slow if it was floating point numbers.
Yeah, the arithmetic would likely be significantly slower and potentially blow up. Yes, there's no question. And the interesting thing here, which actually kind of bothered me in the beginning, was essentially, well, we all know that multiplication of BDDs for multiplication are exponential. They blow up. Why isn't this blowing up? Well, I'm actually not multiplying variable vectors. I'm multiplying numbers that are represented with these variables. The variables are just encoding the numbers. So effectively, it's not really multiplication in terms of the worst possible scenario. That's why they're not blowing up, which is kind of nice to know. And so this can give you the background to S matrices. What I'm going to do now for the rest of the talk is I'm going to give you 3 examples, domains where I've played with them, and use them and see what can you do with this. And one is something I started with Dhas, my Ph.D. students, long gone now in Volvo, and image generation and recognition. And some of you will recognize this from some of the first talks I gave here. Well, a couple of years in here. But basically the idea is to describe the object in a language with symbolic variables, so that we can encode a large family of images by variables effectively. So you can encode large number of circles in various places and sizes and so on and so forth on a canvas, or boxes, or whatever else you want. And by having enough number of variables, we get a very large number of images we can represent. And when I started doing this, we didn't have symbolic matrices at all. So I ended up doing essentially a list of lists of reference variables. So Apple has reference variables now. All the Haskell guys will cringe. And it works, but it's temperamental, let's put it that way. We have to be very careful with writing code for that. And in particular, when you have this symbolic if-then-else expression of reference variables, life gets very interesting, let's put it that way. It can be made to work, as I proved that, but wasn't very elegant, was not very neat. But if you do that, then you can convert a traditional sequential algorithm like Bressenheim's circle drawing algorithm. This is the way you draw algorithm. If you want to draw a circle on the screen, that tend to be effectively some version of Bressenheim's algorithm for drawing it. Effectively, it figures out how to draw them in such a way that they look nice, because the difficulty is, of course, the pixels are not circles, and so you want to place them in the right place. And if you do that, you effectively end up looking something like this into the weird system that I built a while ago. And the key thing here is, notice that we do set pixel, set some reference variables. So this is all sequential code effectively. I guess in Haskell you would just put more on for this, and then life will be at least more elegant, but it will still be ugly. Now, the problem with this was it didn't scale very well. So we sort of left, but we did some up to 64 by 64, but 32 by 32 was probably the practical limit. So it wasn't very big canvases you could draw. You can draw figures of things that looked nice, but wasn't very useful beyond that. So I said, oh, S matrices sounds like a good idea. Well, now this becomes, we take the initial matrix, we return a new matrix, take the new matrix and return yet another one. So we just do a functional style of this. And set is of course not that difficult, because what is set? Well, it's effectively a function that takes a new value and says if the index you're trying to change is equal to the row and the column is equal to the index you're trying to change, then you take the new value, otherwise you take the old value. So that becomes a trivial set function. So effectively, we just let BDDs and magic of if else do all the rest of the work. So now we can generate a lot of things. Here's a fun little example on model size. But we have enough variables that we have 274 billion versions in there. That's a lot of drawings. However, the interesting thing what I wanted to do here was create these kind of potential circles and then say, oh, I'm having an image. It has some circles in it. And I want to find where the circles are and how big they are. And do it in such a way that we don't rely on some approximations that called machine learning. Not sure if that's better or not, but it was interesting to try. So here's something I did last summer. Here's the original image. And if you look carefully, there's a 70 sign there, and there's actually another 70 sign. This screen is horrible.
Same thing as when I'm out driving.
Yes, yes, indeed. So in order to get this, I didn't want to take the image directly to an matrix. I don't think that would work very well. So what you're interested in is, of course, to filter out what are we interested in. In this case, I'm interested in circles that have a red circle around them. The red circle is interesting because those are the speed sign. The speed signs in Sweden, they all have a red circle with a yellow background in the middle and the number in the middle. But at this point, I'm just looking for the finding where the circles are. So if I did a color filter, it just says I want the effective red with a certain range. Here is the red things. This is a nice picture. Some other pictures have large amounts of reds in random pixels here because happen to a red house or something like that. So you get what you deserve sometimes, but that's what you have to be prepared for. And I've done that now. I did a little bit of denoising also because it's just unnecessary garbage in there. So I just look at filter out individual pixels here and there. Just why keep them? And after that, you can then take the image you have, a parameterized image of all the possible circles within a certain size and all the possible locations of the circles and say, okay, overlap with this image and see where is the solution for this one, where they match. What values for the location of the coordinate for the center of the circle and the radius in such a way that it will overlap on the image you see here. And if you do that and then ask it to show me where you found it, you will see it drew a little box. It found that one, and it did find that one.
Well, I don't see this sign nor the box.
Well, that's maybe you should take your driver's license. So I've got done here. This is exploring whether it's practical or not. I don't know. Yeah, better. Is it better? We can do it. Is it better? Yes. Yeah. There we go. Low test. Offset 70. So now you can see the 70. And you have, yeah, and the boxes.
One of them, yeah.
One. Trust me, there is another one. I think it's a display here that's a bit funny. Anyhow, that's one application domain. I think it's interesting. We'll see how far it can go and what we can do with it. The second one.
How long did it take?
Right.
Doing that took about 5 seconds, something like that. So no, I mean, this is of course completely unoptimized code and so forth. By the way, one thing I had to do was when I generate the possible images, I also had to add a filter effectively that says how many pixels do you not have to match? Because you're trying to match 100%, you hardly ever see a sign because there's a leaf in the way, there is some reflection, or the light is reflecting, so the light is not exactly the red you want it to be, that was originally. So you have to accept a certain amount of uncertainty. But here you can parameterize it. You can say exactly how many pixels you have to miss. In the machine learning, you have no choice of that. It will say yes or no, and you don't really know. I can actually justify why it's justifiable. Here I found a circle because it has this many pixels that are red. So there's an explainability here that can be kind of nice. At least it's a potential feature.
So finding the values of the parameters, that requires some kind of search.
Yeah, no, actually,
I'm
just using BDD solving. So you have a BDD for the conditions, and you simply trace down till you get a true the condition.
Oh, I see.
Yeah, they
You
get
don't look
all
for
the-
the truth to BD.
Yeah, exactly.
Ah.
So it's trivial.
Okay,
And you get all of them, by the way.
yes.
And you actually make sure that you don't get more than one, because sometimes you have something that you can match two of them in the same. You want to pick only one, and that's the best one, effectively. Right. Yes. I'm not sure if this is the right application for it, but it's interesting. And using that's matrices. Completely different. Let's change. Since I badmouth machine learning, then of course I should say, then I'm going to try to use it. Of course, machine learning is all matrix operations. We all know that. They basically all do matrix operations, right and left and up and down. So here's an interesting thing, just to show some application the way they're different. I read it before. Here's argmax. That essentially says the vector, you return 1 for each element in the vector that has the maximum value and 0 for all the other one. So we can just write that as a little piece of code, and it checks everything and goes through it and blah blah blah. We find that first we find the maximum, sort of similar to what you're doing is you go on BB and can I make this one the most significant bit one? Yes, if I can. Then what condition does that imply on the rest of them? And then you go to the next bit and say, okay, can I make this one? Yes, here it is. And then what condition does that imply on everyone else? And you just go down the whole way. And that's what we're doing on the max, BB max. And our max is just going through, compute the max, and then if max is V, then it's 1, otherwise it's 0. That's it. That's pretty simple. Max pooling, not terribly interesting. Just, but nevertheless, it's these kind of things. A more interesting one is convolution. Convolution is effectively taking a small little kernel, like say 3 by 3 or 5 by 5, and moving it over the image, and every column by a certain stride, vertical stride and horizontal stride. And at each place, you essentially overlap them and multiply them together and decide which one value you should have, or some of them. Then, of course, that gets through, typically through max pooling that reduces the dimension, and then you usually run relu or some other activation function. That's what you do. The interesting thing here is that we do the same as we did with matrix multiplication. We introduce some extra variables for the little kernel, and we just BV sum over those. The indices for the little extra. So effectively take a little square matrix that we're going to move over. We don't really move it, we just use variables to place it somewhere. And then we just add them up with the same BV sum that we had before. Now for all the little stride. Yeah.
Your kernel is a list of lists instead of an S matrix.
Yeah,
It's unsatisfying.
Yeah, it is. It's actually it's converted to an S matrix immediately.
Oh.
It was just typically it's easier to describe it for testing. It's probably not the right answer. The right answer is it should be an S matrix, of course. That's in this case it was easier to write it this way. So here's a little small neural network, 3 hidden layers, 10 outputs, 32 by 30 image. So it takes the input, multiplied by the first weight matrix, adding the bias matrix or vector, and then apply relu to that. That gives me the first hidden layer. Then do the same thing with that layer to the next one. This is complete network, neural network, relu, and then eventually the argmax to get the 10 outputs. And just to try it out, I generated random matrices for all these things. So in some sense, this is the only possible for S matrices, because BDDs don't like random things, because there's no symmetry, there's no nice things here, so it's about as bad as it gets. And well, it works pretty well. We can build it, we can test it, and if you run it, they took 15 seconds to evaluate a particular input, random input. So
Did you try it on something like the MNIST digit?
I'm working towards that.
Okay.
What I really want to do before that, I want to get the learning training part.
But there are some you could download.
Yeah, I can download, yes. Except that you have to find the integer versions of it. That's not as common. But there are some, yes. I've been playing, we're looking for some of them. I found one that I tried to download, but I couldn't. It didn't generate the answers that I expected it to generate, so I'm not quite sure what that training was. But of course, if we have BDDs at our disposal, why don't we run multiple inputs at the same time? We just encode multiple. And we can training for a whole set of them. In this case, I generated 8 of them at the same time and run them and 103 seconds to evaluate that whole thing. You can play these games now by doing that. An interesting part of that is, of course, normally when you do training, you need to backpropagate. You do gradient descent, so you need to compute the gradient effectively. How much, if I change this weight a little bit, how much does the error increase or decrease if I do that? And for every possible element in the weight matrices or in the bias matrices. Now, theoretically, you could just say, okay, I compute the value for this, and then I add one to one of the weights and compute the whole thing again, and see how much that did, and I do the same thing for another one, and so on and so forth. But of course, there's no way you can do that. You would evaluate, you would have to evaluate the neural network for 147,000 times in this case, just to do the one gradient. So clearly you can't do that. However, we have BDDs. So why don't we just encode the BDD where that one should be added and solve it for that? So here's what I call perturb. Very perturb. And I'm using a little trick. And in the BD package, we have variables A, B, C, D, but we also have hidden behind them a next variable, a next state, often for transitional relations. So there's actually 2 variables, A and AN, everywhere in the variable ordering. So you can take a BDD that depends on A, B, and C and convert it to one that depends on A, N, B, N, C, N. So the new variables, just 3 fresh variables that are in the same location, therefore will be the same size BDD. That's kind of nice, but otherwise exactly the same. So what we can do now is we can simply say if the new variables that are index 1 in the prime version are equal to the row index, we add 1 to it, otherwise it's B. And then we evaluate our neural network for this modified version. And all of a sudden, we get a gradient from the whole thing. So here I did this, perturbed each of the matrices, and ran the whole thing. And in about 3 minutes, or a little bit less than that, we can compute the whole gradient. Now, the interesting thing, we didn't have to do backpropagation at all. So things that makes backpropagation impossible, we could, for instance, have an activation function that's Heaviside. Heaviside has a property that if the result of the sum is negative, it's 0. If the result of the sum is positive, it's 1. So it's discontinuous. It's not differentiable. So backpropagation doesn't work. This one works. You can always do this. So there's a possibility that you can actually get differentials computed for things that you otherwise couldn't do. We don't know. I'm still working on this one. I'm playing with it, but it's an interesting and intriguing. And this ability to do all these kind of tricks and games are to me at least intriguing. So that's my second one.
Okay, it's 11:49.
Yeah.
But you also have come to the best part.
Yes.
Take your time.
Thank you. So, power automation, it's as you said, the best time. Last year I gave a talk here where we did, and Henrik gave another talk later, or before, later I think. Technically what we were doing, we were computing power consumption in combinational logic. So we did uniform distribution that satisfies some predicate, uniform distribution, there were non-uniform distribution, and compute power for those things. We have techniques for all of those things. But the main thing was that they were all combinational. We have no states holding in there. So this now we have to add the sequential part. And the sequential circuit in general looks a bit the same. We have a nice combinational, we know how to deal with that. But we have this feedback loop and it stores state here, flip-flops that stores a state for the next stuff. So in order to compute power of this thing, we also need to know the distribution of the state holding flip-flops. How often are they in a certain state? Do we know that? How do we do that? Well, that depends on if we have a certain state, then it's going to determine what and together with the input will determine what the output will be determined, the input will be turned, it depends on itself. So that makes that a little bit more interesting. So What about something like this? It's a state machine. How often will this machine, if I ran it in random values in random frame forever and ever, which state would it be more often? Is there a state that will be more often or not? So we can actually do this. First thing we do is we compute a transition matrix. And effectively the matrix is said from this state to that state. So if you think of it this way, the transition matrix might say that the probability to go from this state to this state is 20%. Probability to go from this state to that state is 19% or whatever. So we just compute how many possible ways can we go from here to there. And it of course depends on the inputs. The inputs decides where I do a transition from here to there or somewhere else. Then once that's done, we will solve a fixed point equation effectively that says if you have the currently probability of being in some state, you multiply by the transition matrix, you should still be in the same probability distribution. So effectively, the only thing is, of course, you have to make sure that V adds up to 1.0. It's the probability, after all. That took me a while to figure out. Because this is very easy to solve if you don't have that.
Zero.
Zero. And my code gave me zero several times very quickly. However, the problem here is, of course, the transition matrix in itself. If there are n flip-flops, there are 2 to the other states. It blows up very quickly. It gets very, very big very quickly. The matrices get very large. So, of course, there's matrices. I wouldn't talk about it if it wasn't the idea. So here's what I do. So compute this transition matrix, we use symbolic simulation to compute the state relation. That's a traditional thing that simply says there's a predicate that says from this current state, for this input, I can get to this state. Yes or no? That's just standard transition relation in circuit descriptions. Nothing magic or strange with that. What we're now going to do is we're going to say, instead of using a state here, we use a row. This is going to be a row index, and that's going to be our column index. So effectively, from here to here, can we go from there to there? And then we want to see, we want to count how many inputs can it make there. Does that sound like something counting? It sounds like BD sum. In fact, it is. So we just take BD sum of the input variables from the transition relation, and we get the transition matrix. Now, not quite, because we get a count. We don't get a probability. But of course, that's just, we know the total number it can be, so it's just divided by the total number that you can take. That gives you probabilities. So here's a little machine, just to illustrate this. A simple machine. To tell you how it works, the reset signal here, it says it can go here if the reset goes high. But reset also implies by this symbol is that if you're in any other state and reset goes high, it also goes here. I don't draw it because it's too many arrows for that reset. But reset is back, you go back to zero. You go back to what the reset says. That's what it says. And otherwise, it just wander around here. And I1 is R. So if R is high, then it goes to the next state. R. If R stays high, it just circles around with these 4 states. The transition matrix, if you look at, let's say, one of the first entries here, that says, I'm in state S0, and I'm going back to state S0. How many ways can I do that? Well, clearly, if reset goes high, then it doesn't matter what R is. That's 2 already. And finally, there's, of course, I can be here, and R is not true, then I'm not taking the transition, therefore I stay in. So that's the third one. That gives you 3 on this one. Effectively, those are the conditions we take us there. And the whole thing just computed the same way. And I'm not going to go through them, because we don't have time. Now, we can do the same thing, but let's say reset is always false. In other words, it's never reset. What is the probability now? What's the transition matrix for this one? And it's quite different. And effectively, it looks very symmetric. Every state looks pretty much behave the same. And you would expect that, because after all, they're all going to each other. And the count here is just to say why it's 1 here is because basically it's only going to stay, if you're on S0, you're only going to stay in S0 if you don't take that edge. which means that R must be 0, R false, R fine. Here's a slightly more complicated reset and not reset. You see them, they were computed, and if you don't trust me, you can go and look at them. And now we have to solve the problem though. It's a linear system, so Gaussian elimination, right? Gaussian elimination sounds really good, except there's one other problem. You remove one row at a time, and we have 2 to the n rows. Not good, not good at all for any size n. So what we do instead, we do approximation, we do gradient descent. So we compute the error function. That's just what is the error, what's v Tn minus v. And actually, I missed something here. It's in either square it or absolute magnitude. I did absolute magnitude because you want to make sure you don't subtract them from each other. So you just compute some error term. How far away are you from the solution? And then you use you guess initial value, and then you compute the gradient with the technique I talked about in the machine learning part. You take the current value, current guess. You subtract some coefficient, loading coefficient, effectively, how fast you want to jump in the direction of the negative direction of the gradient, and that gives you a next approximation. And you just move yourself, you're climbing down the hill as much as you can. And that's all it takes.
Carl, why can't you just use BDDs to solve this?
Well, in theory you could, but there's a lot of BDDs you can choose here. Because each of these entries in the vector is all in number.
The equation is you can just build a BDD for the equation and say it's v.
Yeah, what I'm trying to say is that each entry in this vector, which is already 2 to the n, has to be a bit vector. It's a number.
There's too many variables.
It's too many variables. Too many, way too many, way too many. However, an interesting idea that I will explore that in have time is that you really don't know what that should be. And it would be actually nice to pick some bunch of variables for that one, to pick a good B. What's the best beta for this iteration? As opposed to heuristics currently, I start with a big beta and it's not getting anywhere or missing it, it's not reducing it. But it doesn't ever jump up again. It's a search problem. So that's possible to do here.
1158.
Yeah, I know. We have integers, so we scale them. Here, just to show you that it's actually correct, it actually exists. You do this, you run the gradient descent on the machine, the computer transition relation. Here is the transition matrix that we saw earlier. And if you compute that, you will see this is the probability you're going to be in different states. And you say, why? Why is it behaving like this? It's very often in S0, way more often than the other ones. Well, that's because there are more ways of getting there. It's almost always going to get there. And it's going to be there much more often. And here, one way to get here is if it came from here and here and here and here. So there's hard to get to S3. Very, very hard to get to S3 in a consistent way. So you can actually look at the number and explain them. So finally, another example. And this is one we saw earlier. Depending if the reset or not reset. Actually, I should do the one before that. I think we have this one here. If you have a reset being on, so now we have reset is always false, then what happens to reset? Well, the matrix is basically the same for everyone. And therefore, the probability to be in any one state is basically a 1/4. There's no difference between them. Here we got this one. Again, same things. I'm not going to talk about it. So, conclusions. I think BDDs provide interesting new approaches for doing all these kind of things. We are just scratching the surface on this. There is a lot of fun things to do here. And this guy is going to do all the power stuff. And he's going to have a lot of fun, I hope, there. The BDDs are not blowing up. I mean, they're big, but they're not impossibly big by any means. I'm not running on the machines we ran at Intel, which typically had 1 terabyte of RAM. That was a common machine we were running for every work. I'm not running on anything remotely as big as that, so modest, can actually live with this. So, what's missing? Well, I want to finish the machine learning training approach. Clearly, we want to do this, we know more of that. In fact, I want to work on all 3 of these more. And now when I'm retiring, I'm going to have time to do that, I hope. Famous last words. Benchmarking. An interesting thing here, I've encoded matrices using binary encoding. The raw index is used binary encoding, and the column is a binary encoded. Would unary encoding maybe be better? More variables, but smaller BDDs maybe? I don't know. That's an interesting possibility. Floating point BDDs, as we talked about earlier, that's definitely interesting. And 8-bit floating points, for instance, that's commonly used now in very large language models. They don't have 32 bits anymore. They didn't have 16 anymore. They have 8 bits, but they still want floating points. So they want a bit of exponent range. Ordering, talked about. Hardware is an interesting one. If you really want to do something, if these all of a sudden BDs are interesting for doing this, maybe that would be worth having hardware. I ran late, so I apologize. Thank you very much. If I want to leave, in otherwise you can stay on questions. Go.
So you have bit vectors that you like using.
Yeah.
Why don't you symbolically index them as well, like you do your matrices?
Yeah. I mean, actually, we have a symbolic list already in the system. The technique you suggested. Yes, we can use that. That's very interesting. Oh.
Yes. Bresenham's line draw algorithm.
Pardon?
Bresenham's circle draw algorithm.
Yes.
You misspelled Bresen.
Oh, yeah. Okay, sorry.
Yeah, it draws 8 pixels every step, not 4. What's that about?
Oh, yeah.
It divides the circle into 8.
Yes, it does. The Resonance have a bunch of different versions of it, and they're getting better and better, more and more
The
complicated.
original one had 8 already.
Yeah, the new ones, I actually have it more recent, but I didn't put that in here because it's twice as large and it doesn't fit. I can't say I can see the difference, to be really honest. They look circles to me, it looks like circles to me. All of them.
So you showed examples of that transition regime.
Yeah.
And you did one example with uniformly distributed inputs, which means the reset signal was 1 half the time.
Yeah.
And then you did another one where you said reset signal is 0.
Yeah.
But I might want to do an analysis where the reset signal is 1% of the time. Can you do that?
Yes, we can. The techniques we developed for a combinational, you can do the same thing, put it in front of it. Then you have a unified, and then you have a de-unifier circuit in between, and then it drives the circuit. So yes, you can. And that also includes, for instance, one thing I didn't show here is that if you have a state that isn't reachable, it will have probability 0. Unless it is built in such a way that it can actually stay there, then it can actually have a time. Then it's basically just the yeah.
Okay, let's end there.
Thank you. Sorry. Yes.